we're going to solve systems of equations, and we have a lot of different methods that we can use to do that. First, we'll start with a graphing method. A system is going to be two or more equations that are related to each other. I mean, that's all. The solution is going to be the ordered pair in which that works for all equations in the system. So here we have our system where x equals 2y plus 1 and 2x plus 2y equals 14 are related to each other. If we want to check if a solution is a system, or if an ordered pair is a solution to the system, what we have to do is just plug it in. So we plug 0 in for x and 1 in for y, and we just check it out. Well, is 0 equal to 2 plus 1? No, it's not. And since this ordered pair doesn't even work for the first equation, it's not going to be a solution to the system. So moving on to the ordered pair 5, 2, we plug that into the equation, and it's 5 equal to 2 times 2 plus 1. Will this 5 equal 4 plus 1? Yeah, it works. That just means that it works for the first equation of the system. We can't crown this ordered pair a solution to the system yet just because it works for the first one. What we need to do is to check it into the second equation as well. So we plug in 5 for x and plug 2 in for y and see if it works out. Well, does 10 plus 4 equal 14? Sure does. So now we found out that this ordered pair is a solution of both equations in the system. Therefore, it's a solution to the system. And graphically, when we think about what's going on, the first line is a linear equation, so that means we could graph a line from it. And that means that every point that's on this line is a solution to the first equation. When we graph the second equation, maybe it looks like this, and every point on this line is going to be a solution to the second equation. What we want our solution to our system is going to be that one ordered pair that's going to be a solution to both equations, and that means it has to be this point of intersection. So if we have our system being y equals 2x plus 1 and y equals negative 1/2 x minus 4, if we want to solve this system, all we have to do is graph the equation. So we graph the first one as a y-intercept of 1 and a slope of 2. So we just kind of keep going through it, through our coordinate system, and graph that line. Now we graph the second line, y equals negative 1/2 x minus 4. That means it has a slope, or y-intercept, of negative 4. We go down 1 over 2, or up 1 back 2, up 1 back 2. And we graph that line. Our solution is going to be this ordered pair that lies on both lines. So it looks like negative 2, negative 3 is our solution. And because we're graphing by hand, we should really kind of check that just to make sure that we didn't get a little sloppy. So we take that ordered pair, negative 2, negative 3, and plug it into the first equation. X is negative 2, y is negative 3, and we check it out. Is negative 3 equal to negative 4 plus 1? Sure is, so it works for the first one. It's not a solution yet. We still have to plug it into our second equation. Is negative 3 equal to negative 1/2 times the x coordinate minus 4. Well, negative 3 equals 1 minus 4. Yep, it works for the second equation too. That means that negative 2, negative 3 is the solution to our system. Sometimes the equations aren't in slope-intercept form, but that's okay. We know how to solve them as well. If we look at the first equation, 8x minus y equals 8, we would, since it's in standard form, we would look for intercepts. So we plug 0 in for x, and we have that negative y equals 8. So that means y is equal to negative 8. And then we plug 0 in for y, we'll have 8x equals 8, so x is going to equal 1. Plotting these points, 0, negative 8 is going to be down here, and 1, 0 is over here. So we just connect the dots, and there's our line. And moving on to the second line, 3x plus 2y equals negative 16. We're going to do the same thing because it's in standard form again. Plug 0 in for x, we got 2y equals negative 16, so y is negative 8. Plug 0 in for y, 3x equals negative 16, so x is negative 16 thirds. Plotting those 2 points, 0, negative 8 is right there. And negative 16/3 is like negative 5 1/3. That's where our point will be. Connect the dots. And there's our line. It looks like this point is the point 0, negative 8 is going to be a solution to our system, so we should plug it in and check. But we don't really need to because we did kind of already do that. And we see that, yeah, 0, negative 8 is a solution to both equations in the system, so we're good. Sometimes you get kind of weird answers for your system. Everything that we've done before has had one solution to the system. Graphing the first equation, 2x plus 5y equals 10, we would use our intercepts again. Plug 0 in for x, 5y equals 10, so y is 2. You plug 0 in for y, 2x equals 10, so x is 5. So y-intercept of 2, x-intercept of 5. Here's our line. Moving on to the second one, we have to do the same thing. You plug 0 in for x, 10y equals 20, means y equals 2. You plug 0 in for y, 4x equals 20, x is 5. We start plotting these points and we're like, hey, the y-intercept's the same, that x-intercept's the same, that means my line is the same, and we got this problem of one line lying right on top of the other line, which means every ordered pair that's a solution to one equation is also going to be a solution to another equation. This system has infinitely many solutions. And we have a couple of special words for that. Anytime that we have a system with at least one solution in it, it's called consistent. So all of the systems that we were dealing with before had one solution, so they were consistent. This system has infinitely many solutions, which is at least one, so it is also consistent. Now, the thing about it is the systems we had before had exactly one solution, so they were independent, consistent, and independent. This system has infinitely many solutions, so there's way more than one solution. So it's not just consistent, but it's also dependent. Now, sometimes with the next example, we'll end up with a system that has no solutions. Check it out. When we look at the first equation, 3x minus 2y equals 6, it's in standard form, so we look for intercepts again. Plug 0 in for x, negative 2y equals 6, so y is negative 3. Plug 0 in for y, 3x equals 6, so x is 2. Y-intercept at negative 3, x-intercept at 2. Here's our line. When we move on to the next equation, plug 0 in for x, negative 2y equals negative 6, y is 3. You plug 0 in for y, 3x equals negative 6, x is negative 2. So an x-intercept of negative 2, a y-intercept of 3, we graph it and we see that these two lines are parallel to each other, so they're never going to intersect. And because they never intersect, that's why it's not going to have any solutions at all. And in this special case, a system with no solutions is called inconsistent. So, to use a graphing method, just graph both lines. Where they intersect is going to be a solution to the system. If there's many solutions, it's consistent and dependent. Only one solution is consistent and independent. And if we end up with two parallel lines, there's no solutions. So it's an inconsistent system.